Max Planck's journey into the world of scientific discovery began in his early years, shaped by a deep curiosity about the natural world around him. Born on April 23, 1858, in Kiel, Germany, Planck's early education was influenced by the intellectual atmosphere of the time. His father, a law professor, and his mother, who was keen on literature and the arts, created an environment in which young Max was exposed to both the sciences and humanities. However, it was his early fascination with physics that led him to choose a career in the subject, setting the stage for a future that would dramatically reshape the field of science. After completing his early education, Planck enrolled at the University of Munich in 1874, where he initially focused on studying mathematics. However, his growing interest in physics soon led him to shift his attention to the discipline. Planck was deeply influenced by the works of other scientists of his time, especially the works of physicists like Helmholtz and Kirchhoff, who were at the forefront of understanding the nature of heat, light, and energy. These topics would become central to Planck's later work. He completed his doctorate at the University of Munich in 1879 with a thesis that explored the theory of heat and its mathematical formulation. At this stage of his career, Planck was already beginning to gain recognition as a promising physicist, though he was still largely unknown to the wider scientific community. His first academic position was as a professor of theoretical physics at the University of Berlin in 1889, where he would spend much of his life. It was at this point that Planck's focus shifted to a problem that had been plaguing the scientific community for decades: the issue of blackbody radiation. Blackbody radiation refers to the type of electromagnetic radiation emitted by a perfect blackbody, an object that absorbs all incident radiation and then re-emits it. Scientists had long been aware that as an object is heated, it emits radiation in the form of light. However, the exact nature of this radiation, particularly at higher temperatures, was not fully understood. Classical physics, based on the laws of thermodynamics and electromagnetism, struggled to explain why the intensity of radiation emitted by objects increased with temperature and shifted from the infrared spectrum to visible light. The problem became known as the ultraviolet catastrophe because classical theory predicted that the radiation emitted at higher temperatures would increase indefinitely in intensity as the wavelength of the radiation decreased into the ultraviolet range. This prediction was not only mathematically unsound but also physically absurd, as no such increase in intensity was observed in reality. This discrepancy between theory and observation was one of the most significant unsolved problems in physics during the late 19th century. Max Planck was drawn into the blackbody radiation problem by his desire to understand the relationship between energy and light. He approached the issue with a fresh perspective, attempting to reconcile the prediction of classical physics with the experimental data available at the time. He began by revisiting the equations of thermodynamics and considering the nature of energy exchange between matter and radiation. However, Planck soon realized that to solve the problem, he would need to make a significant departure from classical thinking. In 1900, after much contemplation and research, Planck introduced a radical new idea: energy is not emitted or absorbed continuously, as classical physics had assumed, but rather in discrete packets. These packets of energy, which Planck referred to as quanta, represented the fundamental units of energy. This hypothesis was a bold step forward, as it introduced a quantum nature to energy that contradicted the long-held belief that energy could be divided infinitely. Planck's hypothesis was initially met with skepticism, as it seemed to defy the principles of classical mechanics. To explain this new theory, Planck derived a mathematical formula for blackbody radiation that incorporated his quantum hypothesis. This formula, known as Planck's law, successfully predicted the observed radiation patterns for black bodies at various temperatures. The success of Planck's law was a turning point in physics, as it provided a solution to the ultraviolet catastrophe and marked the birth of quantum theory. The key to this breakthrough lay in the introduction of Planck's constant, a fundamental value that relates the energy of a quantum to its frequency. At the heart of Planck's quantum hypothesis was the notion that energy is quantized, meaning it is emitted or absorbed in discrete quantities rather than in a continuous flow. This idea not only explained the behavior of blackbody radiation but also suggested that all energy exchanges in the universe might follow the same quantized pattern. This concept would later become the foundation for the development of quantum mechanics, a field of physics that would revolutionize our understanding of the microscopic world. Planck's work on blackbody radiation marked the beginning of a new era in physics, one in which the laws of classical mechanics were no longer sufficient to explain the behavior of matter and energy at the atomic and subatomic levels. Although Planck himself was hesitant to fully embrace the implications of his own theory, he recognized that the success of his quantum hypothesis had opened the door to a deeper understanding of the universe. In the years that followed, Planck's ideas would inspire a new generation of physicists, including Albert Einstein, Niels Bohr, and Werner Heisenberg, who would build upon and extend the concepts introduced by Planck. While Planck's initial focus was on solving specific problems related to radiation and energy, his work laid the foundation for the development of the broader field of quantum mechanics. The principles of quantum mechanics would go on to challenge our most fundamental assumptions about the nature of reality, leading to the development of technologies such as semiconductors, lasers, and quantum computers. Despite his monumental contributions to science, Max Planck remained a humble figure throughout his life. He was not driven by fame or recognition, but by an unrelenting desire to understand the underlying principles of nature. His dedication to his work, even in the face of skepticism and resistance, exemplified the true spirit of scientific inquiry. In conclusion, Max Planck's early career and his breakthrough with the quantum hypothesis were pivotal moments in the history of physics. His work not only solved one of the most pressing problems of the time but also paved the way for a deeper exploration of the quantum nature of reality. The introduction of Planck's constant and the concept of quantized energy marked the beginning of a new era in science, one that would ultimately reshape our understanding of the universe. Planck's contributions, though initially met with skepticism, have had a lasting impact on the field of physics and continue to influence scientific thought to this day. Max Planck's introduction of quantum theory in 1900 did not only solve the specific issue of blackbody radiation, but also led to a profound shift in how scientists thought about energy and the fundamental laws of the universe. His theories were groundbreaking in ways that even Planck himself could not fully anticipate. What he had set in motion was nothing short of a scientific revolution, one that would challenge the very foundations of classical physics and open new realms of exploration in the microscopic world. The idea that energy was quantized, breaking away from the continuous classical view, was both a conceptual leap and a mathematical breakthrough. Planck's insights became the cornerstone of quantum mechanics, a field that would evolve and expand with the contributions of other brilliant minds. At first, Planck's quantum theory was seen as a useful mathematical trick to explain blackbody radiation, and not as a fundamental truth about the universe. Planck himself was initially hesitant to fully embrace the implications of his work. His theory was in stark contrast to the well-established principle of classical mechanics, which had governed physics for centuries. Classical physics, with its deterministic laws of motion, was deeply rooted in the scientific community, and many scientists were reluctant to accept the idea that energy might be quantized. Planck, despite his success, was cautious and felt that his hypothesis was merely a provisional solution to a specific problem. It wasn't until a few years later, when Albert Einstein applied Planck's quantum theory to explain the photoelectric effect, that the true power of Planck's ideas began to be realized. Einstein's work in 1905 demonstrated that light, which was traditionally thought of as a continuous wave, also exhibited particle-like properties. Einstein showed that light could be thought of as being made up of discrete packets of energy, which he called photons. This was a direct extension of Planck's quantum hypothesis, and it provided solid experimental evidence for the idea that energy was indeed quantized. Einstein's work on the photoelectric effect not only confirmed Planck's theory, but also made a crucial contribution to the development of quantum mechanics. Einstein's success with the photoelectric effect also paved the way for further developments in quantum theory. Niels Bohr, a young Danish physicist, extended Planck's work to explain the structure of the atom. Bohr's model of the atom, proposed in 1913, introduced the idea of discrete energy levels for electrons. According to Bohr, electrons could only occupy certain fixed orbits around the nucleus, and they could only gain or lose energy in discrete amounts, corresponding to Planck's quantum hypothesis. This was another significant step toward understanding the quantum nature of the atom and was crucial in shaping the early days of quantum mechanics. While Einstein and Bohr focused on the implications of Planck's work for atomic structure, Werner Heisenberg, another central figure in the development of quantum mechanics, introduced the concept of uncertainty. In 1927, Heisenberg formulated his uncertainty principle, which stated that the position and momentum of a particle cannot both be precisely measured at the same time. This principle was a direct consequence of the probabilistic nature of quantum mechanics, a feature that distinguished it from classical physics. It demonstrated that, at the quantum level, certainty gave way to probability, challenging the deterministic worldview that had dominated science for centuries. Max Planck, although not directly involved in these later developments, remained a vital figure in the scientific community. His role as a mentor and leader at the University of Berlin was instrumental in guiding the next generation of physicists. Planck was not only a brilliant theorist, but he was also a teacher and an advocate for scientific progress. His ability to nurture the talents of young scientists, including Albert Einstein and Niels Bohr, ensured that his legacy would continue to influence the development of quantum mechanics long after his own direct contributions. Planck's contributions were not limited to theoretical physics. His work had far-reaching consequences for the way scientists approached the study of nature. The introduction of quantum theory led to a paradigm shift, with physicists now grappling with the implications of the new quantum worldview. The deterministic, predictable universe of classical physics was replaced by one in which uncertainty and probability played central roles. This shift in thinking was not an easy one, and it took decades for quantum mechanics to be fully accepted by the scientific community. One of the most striking aspects of Planck's legacy is the profound impact his work had on the development of technology. In the decades following the advent of quantum mechanics, scientists began to harness the principles of quantum theory to create new technologies. Semiconductors, lasers, and superconductors, all of which rely on quantum mechanical principles, became central to the development of modern electronics. The very devices we use today, from computers to smartphones, owe their existence to the principles that Planck and his colleagues uncovered in the early 20th century. The quantum revolution, which Planck ignited, directly led to the technology-driven world we live in today. Beyond technology, Planck's work also had a philosophical implication. The development of quantum mechanics challenged long-held views about the nature of reality itself. The idea that particles could exist in multiple states at once, or that their behavior could only be predicted, probabilistically forced philosophers and scientists alike to rethink their understanding of the universe. Planck's work, in this sense, did not simply open the door to new scientific discoveries. It opened the door to new ways of thinking about existence, observation, and knowledge. While Planck's work has been recognized as one of the most important contributions to modern science, it is also a reminder of the incremental nature of scientific progress. Max Planck did not single-handedly revolutionize the world of physics. His success was the result of building upon the work of earlier scientists and providing the foundation for future breakthroughs. His ideas were groundbreaking, but they were part of a larger scientific effort that included the contribution of countless individuals, each adding their own piece to the puzzle of understanding the universe. In conclusion, Max Planck's contributions to the field of physics cannot be overstated. His introduction of the quantum hypothesis in 1900 solved one of the most pressing problems in physics and set the stage for the development of quantum mechanics. Planck's ideas not only transformed the field of physics, but also reshaped our understanding of reality itself. His work continues to influence modern science and technology, and his legacy lies on in the countless innovations that have emerged from the quantum revolution. Planck's ability to think beyond the conventional boundaries of classical physics and embrace new ideas paved the way for the most profound changes in our understanding of the natural world. Max Planck's life and work are often seen as emblematic of the quiet dedication to scientific discovery that drives the world of physics forward. Though his name may not be as well known as that of Einstein or Heisenberg, Planck's contributions were the critical foundation for the development of quantum mechanics, a field that has transformed modern physics and continues to shape new technological advancements today. The second keynote of Max Planck's work that deserves deep examination is his pivotal introduction of Planck's constant, a number so fundamental that it serves as a bedrock for quantum mechanics. This tiny constant, the value that relates the frequency of radiation to its energy, opened up an entirely new view of energy, one that was discrete, not continuous. Planck's constant made quantum mechanics possible and set the stage for the great quantum discoveries that followed. Planck's exploration of black-body radiation was the spark that ignited his lifelong work on quantum theory. The problem of black-body radiation had plagued scientists for years, leading to what was known as the ultraviolet catastrophe. Classical physics could not explain the behavior of radiation emitted by heated objects, especially the fact that, as objects heated up, the radiation emitted increased in intensity. According to classical theory, the radiation emitted at shorter wavelengths, like ultraviolet light, should become infinite at higher temperatures. In reality, however, the observed radiation was not infinite, and classical theory failed to predict the intensity of radiation in the ultraviolet spectrum. Scientists of the day were perplexed. This gap in understanding was a serious challenge to the current models of thermodynamics and electromagnetism. It was Planck who found the way to solve the problem. In 1900, he introduced a hypothesis that radically departed from the classical views of energy. Planck postulated that energy was not emitted or absorbed in continuous amounts, as classical theory suggested, but in discrete packets, which he termed quanta. This radical idea contradicted classical mechanics, where energy was thought to be a continuous variable. Planck's work revealed that energy levels are quantized, and that energy emitted by an object is proportional to the frequency of its radiation, with the proportionality constant being Planck's constant. Planck's discovery was profound, not just because it solved the issue of black-body radiation, but because it set the stage for the quantum revolution that would soon follow. It marked the first real departure from the classical understanding of physics, creating the opening for the development of quantum mechanics. The introduction of Planck's constant and the equation E equal to h nu, where E is energy, h is Planck's constant, and nu is frequency, is one of the cornerstones of quantum theory. This equation led to the realization that the behavior of particles at the atomic level is fundamentally different from the behavior of macroscopic objects, governed by the familiar laws of classical mechanics. This concept of quantized energy was initially seen by many as a mathematical convenience, a way to fix the issue with black-body radiation, but it was quickly recognized as a breakthrough that would change the course of physics forever. In essence, Planck's constant made possible a new way of understanding the universe. No longer were energy levels continuous and infinitely divisible, they were discrete, and the universe at the atomic level operated in a fundamentally different way than the macroscopic world we could observe directly. Although Planck's constant was the key to solving black-body radiation, its implications went far beyond that specific problem. His work laid the foundation for the theory of quantum mechanics, which was further developed by physicists such as Albert Einstein, Niels Bohr, and Werner Heisenberg. Each of these great minds took Planck's quantum hypothesis and applied it to new and more complex problems, resulting in a complete reworking of how scientists understood the physical world. One of the most important implications of Planck's work was the realization that the universe is not fully deterministic. Classical mechanics, which had been the dominant paradigm for centuries, was based on the belief that the universe was entirely predictable if enough information was available. This was the framework that Newton's laws of motion rested upon. However, quantum mechanics, made possible by Planck's work, introduced an element of uncertainty and probability into the equation. It became clear that at the quantum level, it is not always possible to predict the precise state of a particle. This insight would lead to Heisenberg's uncertainty principle, which established that certain pairs of properties, like position and momentum, cannot both be precisely measured at the same time. Furthermore, Planck's constant has far-reaching implications for our understanding of the microscopic world. The idea of energy quanta applies not just to radiation but also to matter itself. The quantum world behaves in ways that defy classical intuition, where particles can exist in multiple states at once, where energy levels are discrete, and where uncertainty reigns. In this strange new world, particles can behave both as waves and as particles, and their behavior is governed by probabilities, not certainties. The applications of quantum theory as founded by Planck's work have transformed technology in ways that were unimaginable when Planck first proposed his quantum hypothesis. Semiconductors, lasers, and computers all rely on the principles of quantum mechanics. The modern world, in which we have access to powerful computers, sophisticated telecommunications, and even technologies like MRI machines and GPS, owes much to the quantum theory that Planck helped create. Without Planck's insight into quantization, much of the technology that defines our everyday lives would not have been possible. But while Planck's work led to groundbreaking advancements in technology, it also changed the way scientists think about the universe. Classical physics had painted a picture of a predictable, deterministic universe where cause and effect governed everything. But Planck's work, followed by the contributions of Einstein, Bohr, and Heisenberg, revealed that the universe at its most fundamental level operates in a probabilistic and uncertain way. This shift in perspective is perhaps one of the most profound changes in scientific thought. In addition to these intellectual breakthroughs, Planck's work also raised important philosophical questions about the nature of reality and the limits of human knowledge. If particles behave according to probability and uncertainty, what does this mean for our understanding of the world around us? Does it suggest that we can never truly know everything about the universe, that there will always be an element of mystery at the quantum level? These are questions that continue to shape not just the field of physics but also the philosophical discussions surrounding science and the nature of reality itself. In conclusion, Max Planck's introduction of the quantum hypothesis and his constant served as the key to unlocking the mysteries of the atomic and subatomic worlds. His revolutionary ideas laid the groundwork for the field of quantum mechanics and transformed our understanding of the universe. Though he was initially hesitant about the full implications of his work, Planck's ideas were later embraced and expanded upon by many of the greatest minds in physics. His contributions continue to shape not only theoretical physics but also the technological advancements that define the modern world. Planck's legacy lives on in the very fabric of our understanding of the universe and in the technologies that have transformed our daily lives. He opened the door to a new, quantum world, one that continues to challenge and inspire scientists to this day. Max Planck's contributions to physics and his pioneering work in quantum theory transformed our understanding of the physical world, fundamentally altering the landscape of scientific inquiry. His introduction of the quantum hypothesis, along with his development of Planck's constant, set the stage for one of the most profound revolutions in the history of science. Part of the significance of Planck's work was the way it opened new ways of thinking about the very nature of energy, matter, and the forces that govern the universe. By solving the problem of blackbody radiation and quantizing energy, Planck demonstrated the inadequacy of classical physics to explain phenomena at atomic and subatomic scales, giving birth to the field of quantum mechanics. As we dive deeper into the lasting legacy of Planck's work, we must explore not only the historical context in which he made his discoveries, but also the subsequent development and implications of his theories. The quantum theory that Planck introduced did not remain static. It was rapidly adopted and expanded upon by scientists like Albert Einstein, Niels Bohr, and Werner Heisenberg, each of whom took Planck's initial steps and pushed the boundaries of what quantum mechanics could explain. In this way, Planck's work evolved into a key aspect of the new physics that revolutionized the 20th century. Planck's law for blackbody radiation provided an accurate mathematical description of how objects emit radiation at different temperatures. His breakthrough was the realization that energy could not be emitted or absorbed continuously, as classical theory had postulated. Instead, energy was quantized. It existed in discrete packets or quanta, which could only take on specific values. This realization helped explain why the radiation emitted by objects did not increase infinitely at shorter wavelengths, as classical physics had predicted. By proposing that energy is quantized, Planck resolved the ultraviolet catastrophe, a problem that had confounded physicists for years. His formula, E equal to h nu, where E is energy, h is Planck's constant, and nu is the frequency of radiation, remains one of the foundational equations of modern physics. At the heart of Planck's quantum theory was the introduction of Planck's constant, a fundamental physical constant that became the cornerstone of quantum mechanics. It defined the relationship between the energy of a quantum and its frequency. While Planck's constant itself is a small number, it has had a vast and far-reaching impact on the world of physics. Planck himself had difficulty understanding the full scope of his own discovery initially, seeing it as a mathematical convenience to explain blackbody radiation. However, over time, it became clear that the quantization of energy had deep implications for the way we understand the microscopic world. The impact of Planck's work on the field of quantum mechanics was immense. His theories challenged the classical notion that the universe operates on deterministic laws of motion, where every event can be predicted if enough information is available. The idea that energy was quantized introduced a probabilistic view of the universe, where the behavior of particles could only be described in terms of probabilities. This uncertainty would become central to the further development of quantum mechanics, as seen in the work of Heisenberg and others. Planck's constant is also deeply connected to the uncertainty principle introduced by Werner Heisenberg in 1927. The Heisenberg uncertainty principle states that certain pairs of properties, such as position and momenta, cannot both be precisely measured at the same time. This concept was a natural extension of the probabilistic nature of quantum mechanics, which Planck's work had helped establish. The uncertainty principle forced scientists to reconsider the very nature of measurement and observation in the quantum world. The idea that particles do not have well-defined positions or velocities, and that we can only speak in terms of probabilities, was a fundamental shift from the classical view of a predictable, ordered universe. While Heisenberg's uncertainty principle had profound implications for the philosophy of science, Planck's work on quantization had more immediate applications in the development of technologies that rely on quantum mechanics. The implications of Planck's constant and the quantum theory it enabled have been far-reaching, especially in the development of technologies like semiconductors, lasers, and computers. These technologies, which have transformed society in the last century, all depend on quantum mechanics. Without Planck's groundbreaking insight into quantization, it is unlikely that the technological advances that have shaped the modern world would have been possible. One of the key turning points in the development of quantum theory was Albert Einstein's work on the photoelectric effect, which demonstrated that light, once thought of as a continuous wave, could also behave like a particle. Einstein extended Planck's idea of quantized energy to the light spectrum, proposing that light consists of discrete packets of energy, or photons. Einstein's theory was supported by experimental data showing that light could be absorbed in discrete amounts by electrons in a metal, thus producing the photoelectric effect. This work confirmed the quantization of energy and directly built upon Planck's theory. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921 and solidified the foundations of quantum theory. As the 20th century progressed, other physicists like Niels Bohr, Erwin Schrödinger, and Paul Dirac extended Planck's ideas to develop the theory of quantum mechanics. Bohr, for example, used the concept of quantized energy levels to explain the structure of the atom. His model of the atom, introduced in 1913, proposed that electrons in an atom could only occupy certain discrete orbits around the nucleus, each with a fixed energy level. This theory explained the spectral lines observed in atomic spectra and represented a key step in the development of quantum mechanics. The advent of quantum mechanics also led to a new understanding of matter. Particles like electrons, which had previously been described as simple points in space, were now understood to exhibit both particle-like and wave-like behavior, a concept known as wave-particle duality. Schrödinger's wave equation, introduced in 1926, provided a mathematical description of how quantum systems evolve over time. These developments showed that at the atomic scale, the rules of classical physics no longer applied, and particles behaved in ways that defied classical intuition. In the decades that followed, the principles of quantum mechanics would be applied to an ever-growing number of phenomena, leading to the development of quantum field theory, which describes the behavior of particles and forces at the most fundamental level. Quantum mechanics has since become an essential part of modern physics, providing the framework for understanding everything from the behavior of atoms to the structure of the universe itself. Max Planck's legacy is not just in the realm of theoretical physics, but also in the impact his work has had on practical technologies. His ideas about quantization have helped shape everything from the development of semiconductors that power our computers to the creation of medical technologies like MRI machines. The technologies of the 21st century are deeply intertwined with the principles that Planck first proposed, demonstrating the profound and lasting influence of his work. Planck's contributions extend beyond just the equations and constants that bear his name. His intellectual courage in proposing that energy was quantized and his willingness to challenge the classical worldview opened new avenues for scientific discovery. He did not just solve the blackbody radiation problem, he fundamentally altered the way we understand the world at its most basic level. In conclusion, Max Planck's work represents a monumental shift in our understanding of the universe. His introduction of quantum theory, including the idea of quantized energy and the introduction of Planck's constant, laid the foundation for the modern quantum mechanics that have revolutionized both science and technology. The ongoing development of quantum theory, spurred by Planck's initial breakthrough, continues to shape the way we view the physical world and has led to transformative technologies that define modern life. Planck's legacy as the father of quantum theory endures in both the abstract realm of scientific inquiry and in the very tangible technologies that continue to drive progress in the modern era. Max Planck's discovery of quantum theory is often regarded as one of the most revolutionary breakthroughs in the history of science. His work laid the foundation for quantum mechanics, a field of physics that challenges and redefines how we understand the universe at its most fundamental level. Planck's work, though initially met with skepticism and confusion, introduced the idea that energy is quantized, that it is emitted or absorbed in discrete packets, or quanta, rather than in a continuous flow. This realization led to the birth of quantum mechanics, a theory that would go on to explain everything from the behavior of subatomic particles to the creation of technologies that have shaped modern society. In understanding Planck's work, it is essential to delve into three major aspects: the introduction of Planck's constant, the formulation of Planck's radiation law, and the transition from classical to quantum physics. Each of these keynotes highlights a pivotal moment in physics, one that drastically changed how we view the universe and the laws that govern it. The first key aspect of Planck's contributions to science was the introduction of Planck's constant, a fundamental value that relates the energy of a photon to its frequency. Planck's constant is incredibly small but immensely important. The constant, denoted by h, is a number that serves as the bridge between the microscopic world of atoms and the macroscopic world of everyday experience. Planck introduced this constant in his work on blackbody radiation in 1900. The issue with blackbody radiation was that classical physics could not explain the radiation emitted by objects when heated to high temperatures. Classical theories predicted that objects would emit an infinite amount of radiation at shorter wavelengths, a prediction known as the ultraviolet catastrophe. Planck's insight was to suggest that energy could not be emitted or absorbed continuously, as classical theory suggested, but in discrete packets of energy, which he termed quanta. He proposed that the energy of these quanta was directly proportional to the frequency of the radiation, with Planck's constant, h, as the proportionality constant. This was a revolutionary idea, because it contradicted the long-held belief that energy could be divided infinitely. With this theory, Planck was able to explain the behavior of blackbody radiation and resolve the ultraviolet catastrophe. Although Planck himself did not fully grasp the broader implications of his discovery, his introduction of the constant marked the birth of quantum mechanics. The second keynote of Planck's work was the development of Planck's radiation law, which mathematically described the emission of radiation by a black body. A black body is an idealized object that absorbs all radiation that falls on it and re-emits it in a spectrum of wavelengths that depend on the temperature of the body. The radiation emitted by a black body follows a specific distribution pattern, which had been experimentally observed but could not be explained by classical physics. Planck's radiation law, published in 1901, provided a precise mathematical formula for the intensity of radiation emitted at different wavelengths and temperatures. Planck's law of radiation was groundbreaking because it incorporated his quantum hypothesis into a classical framework. The formula showed that the energy emitted by a black body at each wavelength was proportional to the frequency of the radiation, with the proportionality constant being h, Planck's constant. The law also introduced the concept of the energy quantum, where the energy of the emitted radiation was quantized, meaning it could only take on specific discrete values. This was a radical departure from the classical view, which treated energy as a continuous variable. Planck's law was able to perfectly match experimental data and provided a solution to the ultraviolet catastrophe, a problem that had puzzled scientists for years. The formula introduced by Planck, E equal to h nu, where E is the energy, h is Planck's constant, and nu is the frequency of the radiation, became one of the most important equations in physics. It marked the first time that the concept of quantization was introduced into the study of energy, laying the foundation for future developments in quantum mechanics. In the years that followed, Planck's radiation law would inspire and influence the work of many other physicists, including Albert Einstein, who applied the quantum hypothesis to explain the photoelectric effect, and Niels Bohr, who used the concept of quantized energy levels to describe atomic structure. The third key aspect of Planck's work was the shift from classical to quantum physics. Prior to Planck's discovery, classical physics, based on the ideas of Newton, Maxwell, and others, governed our understanding of the physical world. Classical physics operated under the assumption that energy, force, and motion could be understood in terms of continuous variables. It was deterministic, meaning that given enough information about the current state of a system, one could predict its future behavior with absolute certainty. However, as physicists began to probe the microscopic world of atoms and subatomic particles, it became clear that classical physics could not fully explain the behavior of matter at these scales. Planck's work and the subsequent developments in quantum theory marked a departure from classical physics and heralded the rise of quantum mechanics, which introduced the idea that at the atomic and subatomic levels, energy is not continuous but quantized. This change in perspective led to a fundamental shift in how we understand the nature of reality itself. The deterministic nature of classical mechanics was replaced by the probabilistic nature of quantum mechanics. In quantum mechanics, the position, momentum, and energy of particles cannot be precisely determined at the same time as articulated in Heisenberg's uncertainty principle. Instead, the behavior of particles is described in terms of probabilities, meaning that there is an inherent uncertainty in how particles will behave. Planck's work was the catalyst for this shift from classical to quantum physics. His introduction of quantized energy levels and his formulation of the radiation law broke the classical view of a continuous, deterministic universe and opened the door to the strange and counterintuitive world of quantum mechanics. The implications of this new view of the universe were profound, not only for physics but also for our understanding of reality. It challenged the long-held belief in the objectivity of the universe and suggested that the act of observation itself plays a role in determining the state of a system. The probabilistic nature of quantum mechanics led to new interpretations of reality, where the concept of a deterministic universe was replaced by one in which probabilities govern the behavior of particles. The transition from classical to quantum physics had far-reaching implications for both the scientific community and society at large. It opened up new areas of research, leading to the development of quantum field theory, quantum computing, and quantum information science. The technology that we take for granted today, such as semiconductors, lasers, and computers, all rely on the principles of quantum mechanics that were first set into motion by Planck's discovery. Additionally, Planck's work inspired philosophers to re-examine the relationship between science and reality, leading to new discussions on the role of observation in the universe and the limits of human knowledge. In conclusion, the three keynotes of Planck's work, his introduction of Planck's constant, the formulation of Planck's radiation law, and the transition from classical to quantum physics, are all foundational pillars of modern physics. Planck's insights broke the classical worldview and ushered in a new era of scientific discovery. His quantum theory not only solved a long-standing problem in blackbody radiation, but also set the stage for a deeper exploration of the atomic and subatomic worlds. The legacy of Planck's work extends far beyond theoretical physics. It has shaped the technological world we live in and continues to inspire new avenues of research. Planck's ability to think beyond the limitations of classical physics and embrace new, revolutionary ideas has cemented his place as one of the most important figures in the history of science. Max Planck's contributions to the scientific community in the late 19th and early 20th centuries forever changed the way we understand the universe, particularly at the atomic and subatomic levels. His groundbreaking work on blackbody radiation, the introduction of the quantum hypothesis, and his formulation of Planck's constant not only solved an important problem in classical physics, but also opened the doors to an entirely new field of physics, quantum mechanics. To explore the magnitude of Planck's work, we can break it down into several pivotal aspects, all of which have had profound and lasting effects on the trajectory of modern science and technology. The introduction of Planck's constant marked the beginning of a new era in physics. For centuries, classical physics had operated under the assumption that energy and matter were continuous. This perspective, which had served science well in many respects, fell short when scientists began studying phenomena at the atomic level. Classical physics, particularly the laws of thermodynamics and electromagnetism, were unable to account for the observed behavior of light and heat at high frequencies. This challenge, known as the ultraviolet catastrophe, was the impetus behind Planck's work on blackbody radiation. Before Planck, scientists had assumed that radiation was emitted continuously, but Planck's revelation that energy was quantized, meaning it could only exist in discrete amounts, solved the puzzle. Planck's constant, denoted as h, represents the smallest possible amount of energy that can be transferred or emitted in a single quantum. This constant played a pivotal role in the development of quantum theory and became an essential part of the mathematical framework that describes atomic and subatomic phenomena. Planck's constant was so small that it initially seemed insignificant. However, its implications were monumental. For example, in the equation E equal to h nu, where E is energy, nu is frequency, and h is Planck's constant, the relationship between the energy of a quantum and the frequency of radiation was established. This equation provided the foundation for understanding the energy transfer in radiation, which, in turn, laid the groundwork for the development of quantum mechanics. Although Planck did not initially recognize the full implications of his work, the idea of energy quantization became a cornerstone for the next generation of physicists. Albert Einstein, for example, used Planck's quantum hypothesis to explain the photoelectric effect, showing that light, which was traditionally viewed as a continuous wave, also behaved as though it consisted of particles. Einstein's work in 1905 demonstrated that light could be absorbed in discrete packets or photons, and that energy transfer occurred in quantized amounts. This extension of Planck's ideas would go on to earn Einstein the Nobel Prize and significantly advance the field of quantum mechanics. The second major aspect of Planck's work that is critical to understanding the quantum revolution is Planck's radiation law. Classical physics, specifically the theories of electromagnetism and thermodynamics, could not explain the radiation emitted by a black body, an idealized object that absorbs and emits all types of electromagnetic radiation. As temperature increased, classical theory predicted that the emitted radiation would increase indefinitely at shorter wavelengths, specifically in the ultraviolet spectrum. This discrepancy between theory and experiment, known as the ultraviolet catastrophe, was a major problem in late 19th century physics. Planck's radiation law solved this problem by introducing his quantum hypothesis into the equation. In 1900, Planck formulated an equation that accurately described the intensity of radiation emitted by a black body at different temperatures. His law showed that the amount of radiation emitted by a body at any given temperature was proportional to the frequency of the radiation, but with a correction factor that accounted for the quantization of energy. Planck's law not only explained the observed radiation from black bodies, but also introduced the concept of quantized energy levels, a key idea that would later be expanded upon in the development of quantum mechanics. Planck's radiation law was revolutionary because it brought together classical thermodynamics and the new quantum ideas he had introduced. The mathematical form of Planck's law showed that energy levels could only take specific, discrete values, and this quantization was critical in explaining why black bodies emitted radiation in the way they did. The success of Planck's radiation law was immediate, as it matched experimental data that had eluded classical theory. However, Planck himself was initially hesitant to fully embrace the implications of his discovery, viewing it as a mere mathematical solution to a specific problem rather than a radical new way of understanding the universe. In contrast, the scientific community soon recognized the broader implications of Planck's work. Planck's radiation law became one of the foundational principles of quantum theory. The introduction of quantized energy levels provided the mathematical and conceptual framework for later developments in quantum mechanics, including the work of scientists like Niels Bohr, who applied quantization to explain atomic structure, and Werner Heisenberg, who introduced the uncertainty principle. The third significant aspect of Planck's work was the dramatic shift from classical to quantum physics. Before Planck, the classical worldview dominated the field of physics. In classical mechanics, the universe was viewed as a machine governed by deterministic laws of motion. If we knew the positions and velocities of all particles at a given moment, we could predict their future behavior with perfect accuracy. This view, rooted in the work of Isaac Newton and other classical scientists, was immensely successful in explaining the behavior of everyday objects. However, when applied to atomic and subatomic systems, classical mechanics failed to provide accurate results. At the microscopic level, particles like electrons did not behave according to the deterministic rules of classical physics. The introduction of Planck's constant and the concept of energy quantization changed everything. The shift from classical to quantum physics was not instantaneous. At first, many physicists resisted the idea that energy was quantized, viewing it as a mathematical trick rather than a real physical phenomenon. However, as more experimental data emerged, particularly Einstein's explanation of the photoelectric effect, it became increasingly clear that classical physics was inadequate to explain the behavior of light and matter at the atomic scale. As a result, quantum mechanics began to take shape as a new branch of physics. Quantum mechanics introduced a probabilistic view of the universe, where particles could not be precisely located or predicted in the same way that classical physics described macroscopic objects. Instead of focusing on deterministic trajectories, quantum mechanics described systems in terms of wave functions and probabilities. This shift to a probabilistic interpretation of the universe was one of the most profound changes in the history of science. One of the key consequences of the development of quantum mechanics was the realization that classical physics was only an approximation of a much deeper and more complex reality. Classical physics worked well for macroscopic objects but could not accurately describe the behavior of particles at the atomic and subatomic levels. Quantum mechanics, on the other hand, provided a framework for understanding the strange and counterintuitive behavior of particles, such as wave-particle duality, the uncertainty principle, and quantum entanglement. Planck's contributions to quantum mechanics, though initially seen as a way to solve specific problems, ultimately led to a profound rethinking of the laws of nature. The quantum revolution, which Planck's work helped ignite, led to the development of technologies that are fundamental to our modern world, such as computers, semiconductors, lasers, and medical imaging devices. Additionally, the philosophical implications of quantum theory continue to shape our understanding of reality and the limits of human knowledge. Max Planck's legacy is not just in the formulas and constants he introduced, but in the way his work transformed our understanding of the universe. His insights into the quantization of energy, his formulation of Planck's radiation law, and his role in the transition from classical to quantum physics have had a lasting impact on science and technology. Through his work, Planck opened the door to a new world, one that challenges our intuitions about the nature of reality and has led to some of the most exciting and transformative discoveries in modern science. The quantum world, as strange and enigmatic as it is, owes its existence to Max Planck, whose pioneering work continues to inspire and shape the future of physics. Max Planck's groundbreaking contributions to physics did not merely introduce new equations or concepts, but redefined the very framework through which we understand the universe. One of his most significant achievements was the introduction of the quantum hypothesis, which fundamentally changed how scientists approached energy and matter. Prior to Planck, classical physics operated under the assumption that energy was continuous and could be divided into infinitely smaller parts. However, Planck's work on blackbody radiation in 1900 showed that energy is actually quantized, meaning it exists in discrete units or quanta. This idea was revolutionary, as it contradicted classical physics, which had assumed that energy could be divided endlessly. Planck's quantum hypothesis not only solved a long-standing problem in physics, but also laid the groundwork for the development of quantum mechanics. The second crucial contribution Planck made was the formulation of Planck's radiation law. This mathematical law described the spectral distribution of radiation emitted by a perfect black body, an idealized object that absorbs and emits all electromagnetic radiation. Classical physics had failed to explain the observed radiation patterns, particularly at short wavelengths. Planck's radiation law resolved this by incorporating his quantum hypothesis, showing that radiation was emitted in quantized energy levels. His law accurately predicted the observed intensity of radiation emitted by black bodies at different temperatures, something that classical theories had been unable to do. This formula, combined with the concept of quantized energy, became a cornerstone of quantum theory and showed that energy levels in radiation were not continuous, but discrete, based on frequency and Planck's constant. A third key element of Planck's work was the introduction of Planck's constant, a fundamental physical constant that plays a central role in quantum mechanics. Planck's constant connects the energy of a quantum of radiation to its frequency through the equation E equal to h nu, where E is energy, h is Planck's constant, and nu is the frequency. This constant became a fundamental value in the study of the quantum world, marking the difference between classical and quantum physics. Planck's constant was not just a number, it represented the smallest possible amount of energy that could be transferred or emitted, serving as a bridge between the microscopic world of atoms and the macroscopic world that we observe in our everyday lives. Its introduction was instrumental in the development of quantum theory, influencing the work of later physicists like Albert Einstein, Niels Bohr, and Werner Heisenberg. Finally, Planck's contributions went beyond just theoretical physics to spark a dramatic shift in the entire scientific paradigm, especially regarding the shift from classical to quantum mechanics. Classical physics, with its deterministic view of the universe, was inadequate to explain phenomena at the atomic and subatomic levels. The idea that particles could exist in multiple states, or that their positions and velocities could not both be precisely measured at the same time, a concept that would be later formalized in Heisenberg's uncertainty principle, emerged from Planck's work on quantization. This probabilistic view of particles marked a departure from the predictability of classical mechanics, replacing certainty with the concept of probability. Planck's work laid the foundation for a completely new understanding of the universe, one where uncertainty, wave-particle duality, and quantization became central principles, marking the birth of quantum mechanics and paving the way for technologies such as semiconductors, lasers, and quantum computers. The profound philosophical and technological shifts introduced by Planck's work have continued to shape the course of science and modern technology in ways unimaginable during his time. Max Planck's contributions to the development of quantum theory were pivotal in reshaping the understanding of the natural world. His work not only solved long-standing issues in physics, but also laid the groundwork for revolutionary advancements in both theoretical physics and technology. Among his most significant contributions was the introduction of the quantum hypothesis, which fundamentally changed the way scientists thought about energy. Before Planck, energy was believed to be continuous, flowing in a smooth, uninterrupted manner. However, Planck's exploration of blackbody radiation revealed that energy is actually quantized, existing in discrete packets or quanta. This insight was a profound departure from classical physics and established the foundational principle of quantum mechanics. It shifted the scientific community's view, showing that the atomic world operates in a fundamentally different way than macroscopic objects. Planck's radiation law was another critical breakthrough in understanding how energy is distributed in the form of radiation emitted by a perfect black body. Prior to this, classical physics had failed to explain the observed intensity of radiation emitted by black bodies, especially at high frequencies. The theoretical predictions of classical mechanics led to the ultraviolet catastrophe, which suggested that energy would increase infinitely at shorter wavelengths, something never observed in nature. Planck's radiation law successfully solved this problem by introducing the idea of quantized energy levels. It demonstrated that energy emitted by black bodies is not continuous, but discrete, proportional to the frequency of the radiation. This law not only resolved a major discrepancy in classical physics, but also provided the first clear evidence of energy quantization, a key tenet of quantum theory. In addition to his work on black-body radiation, Planck's introduction of Planck's constant became one of the most important constants in physics. This constant, denoted by h, links the frequency of radiation to its energy through the equation E equal to h nu, where E is energy and nu is frequency. Planck's constant serves as a fundamental element in quantum mechanics, providing a bridge between the microscopic world of particles and the macroscopic world we can observe. The significance of Planck's constant is not just mathematical, it represents the smallest possible quantum of action in the universe, meaning that energy is exchanged in discrete amounts, not continuously. This idea would lay the foundation for the development of the entire field of quantum mechanics, influencing subsequent research by physicists like Albert Einstein and Niels Bohr. Moreover, Planck's work was integral to the shift from classical physics to quantum mechanics, a transition that altered the very way we understand the universe. Classical physics, with its deterministic and continuous nature, had dominated science for centuries, providing accurate descriptions of the macroscopic world. However, when applied to the atomic and subatomic levels, classical physics failed to explain many phenomena. Planck's introduction of energy quantization shattered the classical paradigm, forcing scientists to reconsider the fundamental nature of reality. Quantum mechanics introduced a probabilistic view of the universe, where particles could no longer be precisely located or predicted in the same way classical objects could. Instead of determinism, quantum mechanics proposed that the state of a particle could only be described in terms of probabilities. This shift from a deterministic universe to a probabilistic one marked a profound change in our understanding of science and reality. Finally, Planck's work had far-reaching implications beyond theoretical physics, especially in the realm of technology. The principles of quantum mechanics, as pioneered by Planck, have become the foundation for modern technologies such as semiconductors, lasers, and computers. These technologies, which have become integral to modern life, owe their existence to the quantum theory that Planck's discoveries set in motion. The development of quantum computing, for example, is a direct result of the principles of quantum mechanics, and it promises to revolutionize fields like cryptography, medicine, and artificial intelligence. Planck's contributions to quantum theory were not just academic, they have directly influenced the technological advances that shape our daily lives. His ideas continue to drive innovation and exploration in both science and technology, demonstrating the lasting legacy of his work. Max Planck's groundbreaking contributions to physics laid the foundation for a revolution in our understanding of the universe. His work on quantum theory, especially his introduction of energy quantization, changed the course of modern science and technology. One of the key elements of Planck's work was his introduction of the quantum hypothesis, which proposed that energy is not emitted or absorbed continuously, but in discrete packets called quanta. This idea challenged the classical notion of continuous energy flow, which had been the prevailing understanding in physics. Planck's hypothesis provided the first step toward the development of quantum mechanics, a field that would later revolutionize how scientists viewed the behavior of matter and energy at the atomic and subatomic levels. This insight not only solved the problem of black-body radiation but also opened up entirely new ways of thinking about energy, light, and matter. A second key aspect of Planck's work was his formulation of Planck's radiation law. Prior to this, classical physics had failed to explain the spectral distribution of radiation emitted by a black body, a theoretical object that absorbs and emits all forms of electromagnetic radiation. Classical theory predicted that radiation intensity would increase infinitely and the wavelength decreased, which led to the so-called ultraviolet catastrophe. Planck's radiation law resolved this paradox by introducing the idea that radiation is emitted in discrete energy levels, proportional to the frequency of the radiation. His formula perfectly matched experimental observations and marked the first practical success of quantum theory. The law also demonstrated that energy, rather than being continuous, is emitted in quantized amounts. This discovery proved crucial for the development of quantum mechanics and was a pivotal moment in the history of physics. Planck's constant, which he introduced as part of his work on black-body radiation, is another fundamental element of his legacy. Represented by the symbol h, Planck's constant defines the relationship between the energy of a photon and its frequency. This constant is central to quantum mechanics and represents the smallest possible unit of action in the universe. The equation E equal to h nu, where E is the energy, h is Planck's constant, and nu is the frequency, shows that energy is proportional to frequency. This relationship has become one of the most fundamental equations in physics, and the constant itself is one of the most important and well-known physical constants. Planck's constant bridges the gap between the macroscopic world, which classical mechanics describes, and the microscopic world of quantum phenomena. Its introduction marked a turning point in the development of quantum theory and made possible the study of atomic and subatomic particles in a new light. In addition to his theoretical contributions, Planck played a critical role in the shift from classical to quantum physics. Classical physics, with its deterministic laws of motion, worked well for explaining the behavior of large objects, but failed to account for the strange and counterintuitive phenomena observed at the atomic level. The transition from classical to quantum physics was marked by the realization that the universe operates differently on the microscopic scale. Planck's introduction of quantized energy challenged the classical worldview, which assumed that energy was a continuous and predictable quantity. This realization laid the groundwork for the probabilistic nature of quantum mechanics, which was further developed by other physicists like Albert Einstein, Niels Bohr, and Werner Heisenberg. The shift to quantum mechanics marked the beginning of a new era in physics, where uncertainty and probability replaced certainty and determinism. The philosophical implications of Planck's work were also profound. By introducing the concept of quantization, Planck fundamentally changed the way scientists understood the nature of reality. Classical physics had assumed that the universe could be fully described by deterministic laws, where the future could be predicted with perfect accuracy. However, Planck's work, and the developments that followed, showed that at the quantum level, particles and energy behave in ways that are not entirely predictable. This uncertainty, encapsulated in Heisenberg's uncertainty principle, is a central feature of quantum mechanics. The probabilistic nature of quantum mechanics suggests that the universe is not entirely deterministic, and our ability to measure or predict the behavior of particles is fundamentally limited. This shift in perspective had far-reaching implications not only for science but also for philosophy, as it raised questions about the nature of reality and our ability to truly understand it. Finally, Planck's contributions to quantum theory have had lasting technological implications. The principles of quantum mechanics, which he helped establish, have led to the development of numerous technologies that define the modern world. Semiconductors, lasers, and computers, which are all based on quantum mechanical principles, have transformed industries ranging from telecommunications to healthcare. Planck's work on energy quantization laid the foundation for the development of the transistor, a key component in modern electronics. Quantum mechanics also plays a central role in the development of technologies such as MRI machines, which are used in medical diagnostics, and quantum computers, which are still in the early stages but hold the potential to revolutionize computing. Planck's legacy lives on in the technologies that shape our daily lives, showing that his work was not only of theoretical importance but also had profound practical application. In conclusion, Max Planck's work on quantum theory was one of the most significant milestones in the history of science. His introduction of energy quantization, the formulation of Planck's radiation law, the introduction of Planck's constant, the transition from classical to quantum physics, and the philosophical implications of his work have all had a lasting impact on our understanding of the universe. Moreover, his ideas have led to the development of groundbreaking technologies that continue to shape the modern world. Planck's contributions paved the way for the quantum revolution and forever changed the way we perceive the laws of nature, both in the microscopic and macroscopic worlds. Max Planck's work stands as one of the most significant turning points in the history of physics. His contributions to the development of quantum theory revolutionized the way we understand the behavior of energy and matter at the atomic and subatomic levels. Planck's insights, particularly his introduction of energy quantization and Planck's constant, laid the foundation for what would become the most important development in physics in the 20th century, quantum mechanics. Throughout his career, Planck not only solved long-standing problems in classical physics, but also opened up new avenues of scientific exploration, which would eventually lead to the development of quantum theory. His ideas are as crucial today as they were when first introduced, and they continue to shape the way we interact with and understand the universe. The first key aspect of Planck's legacy is his introduction of the quantum hypothesis. In the late 19th century, scientists were struggling to explain the phenomenon of black body radiation, particularly at high frequencies. Classical physics could not explain why the intensity of radiation emitted by objects increased with temperature and shifted to shorter wavelengths. Planck's hypothesis, introduced in 1900, was revolutionary because it proposed that energy is not emitted or absorbed continuously, as classical physics had assumed, but in discrete packets called quanta. This breakthrough idea laid the groundwork for the development of quantum mechanics, and it was crucial in solving the ultraviolet catastrophe, a long-standing problem in thermodynamics. The concept of energy quantization reshaped the way scientists thought about energy, showing that, at the atomic level, energy behaves fundamentally differently from what was previously assumed. The second significant contribution was Planck's formulation of his radiation law. Planck's radiation law accurately described the radiation emitted by a black body, an idealized object that absorbs and emits all radiation. Classical physics had failed to predict the distribution of radiation emitted by black bodies, especially at high frequencies. Planck's law solved this issue by introducing the concept of quantized energy. The law stated that the energy emitted by a black body is proportional to the frequency of the radiation, with a correction factor that accounts for the quantization of energy. This law not only provided a mathematical formula to match experimental data, but also validated the idea that energy is quantized, marking a pivotal moment in the history of physics. Planck's radiation law was one of the first successful applications of quantum theory and played a central role in ushering in the era of quantum mechanics. A third key aspect of Planck's work was his introduction of Planck's constant, a fundamental physical constant that links the energy of a photon to its frequency. Planck's constant is represented by h and is one of the most significant constants in physics. In his equation, E equal to h nu, where E is the energy of a quantum, nu is its frequency, and h is Planck's constant. This simple yet profound relationship provided a mathematical framework for understanding energy in the quantum world. Planck's constant signified that energy exists in discrete, quantized amounts rather than as a continuous flow. This constant became one of the foundational pillars of quantum mechanics, helped bridge the gap between the microscopic world of atomic particles and the macroscopic world that classical physics had previously explained. The fourth key contribution was the shift from classical to quantum physics, facilitated by Planck's work. Before Planck, the scientific community relied on classical physics, which was based on the deterministic laws of motion formulated by Newton. Classical physics worked well in explaining the behavior of large objects but failed to describe the behavior of particles at the atomic and subatomic levels. Planck's introduction of quantized energy and his radiation law marked the beginning of the transition to quantum mechanics, a field that embraces uncertainty, probability, and wave-particle duality. This transition challenged long-standing beliefs in determinism and introduced a new way of thinking about the fundamental nature of reality. The quantum world was shown to be probabilistic, where particles could exist in multiple states at once, and their behavior could only be predicted with a certain degree of probability, not certainty. The fifth important aspect of Planck's work was his influence on later developments in quantum mechanics. While Planck was initially cautious about the implications of his own theory, his ideas would inspire and guide future physicists, such as Albert Einstein, Niels Bohr, and Werner Heisenberg, who expanded on Planck's quantum hypothesis. Einstein's work on the photoelectric effect, for example, extended Planck's ideas to the realm of light and demonstrated that light behaves as both a wave and a particle. Bohr's model of the atom, which introduced the concept of discrete energy level for electrons, was directly influenced by Planck's quantization of energy. Heisenberg's uncertainty principle, which stated that the position and momentum of particles could not both be precisely measured at the same time, was a natural extension of the probabilistic nature of quantum mechanics. Planck's ideas served as a catalyst for these subsequent developments, helping to form the bedrock of modern quantum theory. The sixth keynote of Planck's work is his pivotal role in the philosophical implications of quantum theory. Planck's work not only changed the landscape of physics, but also had profound philosophical consequences. His discovery that energy is quantized, and that the behavior of particles at the atomic level is probabilistic challenged a deterministic worldview that had been dominant in classical physics. This shift introduced the idea that uncertainty and probability are inherent features of the universe, leading to a re-examination of the relationship between the observer and the observed. The uncertainty principle, for instance, suggested that the act of observation itself affects the state of the system being measured. These philosophical questions about the nature of reality continue to be a topic of discussion among both physicists and philosophers. Planck's contributions made it clear that the universe is much stranger and more complex than previously understood. Finally, Planck's contributions to quantum theory have had lasting practical applications in modern technology. The principles of quantum mechanics, as pioneered by Planck, have become the foundation for numerous technological advancements, including semiconductors, lasers, and quantum computers. The quantum theory Planck helped establish is at the heart of modern electronics, telecommunications, medical imaging, and many other fields. Quantum technologies such as semiconductors and transistors have revolutionized computing, while lasers, which rely on the principles of quantum mechanics, are used in everything from communication to surgery. Even though Planck did not live to see the full extent of these technological advancements, his work directly influenced the development of technologies that have shaped the modern world in ways that continue to expand today. In conclusion, Max Planck's work in the early 20th century introduced concepts that radically transformed our understanding of the universe. His ideas on energy quantization, his radiation law, Planck's constant, the shift from classical to quantum physics, his influence on subsequent physicists, the philosophical implications of quantum mechanics, and the practical applications of quantum theory all contributed to the quantum revolution that reshaped science and technology. Planck's legacy is not only in the theories and equations that bear his name, but in the way his work redefined the laws of nature and opened new avenues for both scientific exploration and technological innovation. His contributions continue to resonate in the fields of physics, technology, and philosophy, cementing his place as one of the most influential scientists in history.